before I turn it over to our speakers, I'm going to invite John Griffith from University of Colorado to give a brief overview of MOSAiC. So John, take it away.
Great. Hi, everyone, and thanks to Liz for organizing this MOSAiC month. It's been great working with her. It's been great connecting so many to the MOSAiC expedition. Just wanted to start with some quick background. The 2019-2020 MOSAiC expedition was one of the largest Arctic research expeditions ever conducted, with more than 500 scientists from 20 nations participating. The goal is to better understand the changing Arctic climate system by studying all aspects of the ocean, atmosphere, sea ice processes. The expedition began in September of 2019 when the research vessel Polarstern, along with the supply vessel Academic Fedorov, sailed north into the Central Arctic, the Polarstern in search of a suitable ice flow with which to attach to. Once attached, scientists deployed a series of instruments adjacent to the ship. The Fedorov, that supply vessel, set up a series of research stations up to 50 kilometers away from that central observatory, the Polarstern. Together, the scientists, the ship, these instruments drifted along the transpolar current for the next year, gathering these important climate data sets. While the field portion of the MOSAiC expedition last week, we're really excited about the future of MOSAiC, the data analyses, the important discoveries. They're just beginning. So without further ado, I'd like to turn it over to the speakers to tell you a little bit more about their work and their experience.
Thanks, John. So we're going to have all 5 lightning talks in a row, and we'll have time for questions at the end. And we are having the speakers in order of the MOSAiC legs, so basically chronological order. I'm going to give each speaker a wrap-up warning at 4 minutes and 30 seconds. And again, I'll have the chat closed during the talks, and then during the Q&A, it'll open up again. So our first speaker is Ying-Chi Fang, who is a physical oceanographer and postdoctoral scientist in the section of physical oceanography at of the polar seas at the Alfred Wegener Institute. His career focuses on using knowledge of physical oceanography to explore important information hidden in the data. So he was on MOSAIC's Team Ocean during MOSAiC Leg 1. So Fang, you can take it away.
Is my voice okay now?
Sounds great. Okay.
So good morning, good afternoon, good evening, everyone. This is my honor to share our new findings, to share something new from MOSAiC. And today I will give you some story in Leg 1. So briefly mention about the Leg 1 of MOSAiC. So we departed from Tromsø, Norway in September and all the way to the Central Arctic Ocean. And in some date in late September, and then we in October, and then we begin our drifting. So here you will see these little dashed squares. This is the range of the Leg 1. So there are 2 major tasks in Leg 1. So on Fedorov, we deployed the so-called distributed network. And on Polarstern, the main goal is to find a suitable ice flow and layer we build up, we call it Central Observatory, CO. So what is CO plus DN? So this is a conceptual view to regard how it looks like. So pretty much you can think Polarstern is our sun in the center of the solar system. And for the distributed network, we aim to deploy a lot of observational platforms around it, okay? So briefly, we have 3 large sites, L sites, and 8 medium sites, we call M sites, plus a lot of various different types of buoys. So this is our project, and we call it Salinity Ice Tailor Buoy, or you can just call it CTD buoy. So it is a system that it has a service unit we deploy on the ice, and with 5 temperature and salinity sensors that is mounted along a 100-meter long tailor. And this is the picture my colleague Mari Hoppmann and I, we deploy into the ocean. So this is our ice camp on the Central Observatory. We call it Ocean City. When you go into the Ocean City, you will see such very interesting instruments. We call it CTD, and here we have this specialized sensor. It's aiming for measuring very finer scale in the water column. So this is how it looks like when you deploy a CTD into the ocean. So the main goal is we want to have a profile for the whole water column, and this way we can have an idea how the water is vertically distributed in the ocean. So besides our ship Polarstern, we also make a hole on the ice. This is a big hole. It's about 3 meters by 3 meters, and we deployed the CTD on Polarstern into this hole. So if you combine those data sets all together from Central Observatory CTD, those squares, with all our available CTD buoys, this is the data set, how it looked like. Very amazing. A lot of data set in this kind of not so big area. So if you make a simple plot just to plot the upper 110 meter, all the CTD data together, you will realize there is a depth range where the density have a very sharp jump. For this depth range, we call it halocline, okay? I just give you an idea. There is a very big event, a very special event in Lake One. We call it our storm event. So it started from the 16th to 19th of November 2019. When it comes, you will realize that the air temperature, it increased from -30 all the way to about -70 to -7 degrees. And during this time, we have a very strong wind, up to 20 meters per second, very, very strong. And when it happened, everything was screwed up. So you will find out in the Central Observatory, our main ice floe was broken. And here's another picture.
30-second warning.
Okay, and here is another picture, you know, the Ocean City, and there's a big opening here. And I want to point out that during the storm, before and after, and I make such plot, I call it wave number spectra. And what I find out is before and after the storm, if you plot out the slope of the spectra, it only changed in the halocline depth. Why? So I made this simple cartoon. During the storm, your ice is broken and the ocean is interacting with the atmosphere, but it looks like those mixing processes, it only happens within the halocline depths and it did not penetrate to deeper depths. Why? And this is some interesting problem for us, for our team, that we want to continue. So I give my talk to Michael. Thank you very much.
Thank you, Sang. So next up, we have Michael Angelopoulos, who is a PhD student at the Alfred Wegener Institute, researching subaquatic permafrost beneath thermokarst lakes, lagoons, and seas in the Siberian Arctic and along the Alaskan coast. He is particularly interested in salt transport impacts on subaquatic ice-bearing permafrost evolution and gas movement in the sediment. At AVI, he also took part in MOSAiC, where he spent 4 months on the Polarstern icebreaker, exploring sea ice and methane cycling in the Arctic Ocean. So Michael, I will turn it over to you now.
Okay, thank you very much for the introduction. Yes, my PhD is on subsea permafrost, but that is not what this talk will be about. I had the privilege of joining the MOSAiC expedition researching methane cycling in the Arctic Ocean. So this backdrop here is one of my favorite pictures. It highlights the isolation of our expedition, the Polarstern in the bottom right and the moon in the top left being the 2 light sources in the polar night. So our main objective in the biogeochemistry team is to quantify and understand the seasonal processes of climate relevant gases like methane in sea ice. So basically what we're after is we want to understand how sea ice controls the exchanges of gases between the atmosphere and the ocean. And in an era of declining minimum sea ice extent, what does that mean? So the great thing about MOSAiC is that it's a year-long expedition, and we can get a time series over the course of a whole year. So we would go out to different sites every week and measure the temperature of the ice, how much salt there is in the ice, and the gas content. So let's jump right into it. This is a short video of our coring activities. You can see that my colleague Levong is coring the ice, and I'm on the ice surface here clearing away the snow. So we had a lot of different sites, and we found some interesting things. For example, we found sediment in the ice, mud. Oh my goodness, how could that be? So if you look in the bottom right, there's some very, very small silt inclusions that you can see. And then we would cut these ice cores and we would filter out these sediment particles. And you can see in the bottom right that this is what these filtered samples look like. So this tells us, gives us an indication that our ice was once in contact with shallow waters close to the coast. So one paper that recently got published by the Fedorov expedition leader Thomas Krumpen confirms this by using satellite imagery to trace back the origin of our ice flow. So in September 2019, if you look at the image on the right, you'll see that we were at about 85 degrees north. And if we track the movement of our flow back in time, we find that in December 2018, this ice flow started to form just north of the New Siberian Islands in Siberia. So during the flow's trajectory, the flow ice partially melted, but it had survived this summer period. So with Kerry, who is the next presenter, in October 2019, we started to core in the distributed network that Fang talked about. And you can see that in October 2019, that there are two main layers in the sea ice. We have an impermeable layer on top that's quite solid and transparent and cold. And then towards the bottom, we have a more permeable layer that has a lot of channelized structures. So looking at this, we can begin to speculate that this lower half of the ice would be more conducive to gas flow. So what we want to do over the course of a year is then see how these permeable and impermeable structures will change from autumn to the summer. And not just looking at structure, we also want to quantify the permeability of the ice. So we would go out in the field and we would take temperature measurements.
So 4.9. 4.9.
Another 5.
5.1.
So we drill small holes in the ice core and stick in a temperature probe.
Yeah.
And then try to write in the field book at -40. Extraordinarily difficult.
Your time warning.
Thank you. And we would also measure the salinity of the ice. And then with those two parameters, as well as the density of the ice core, we could try and get an estimation of how much brine there is in the ice. So this is just unfrozen liquid that's saline below 0 degrees Celsius. So just to give you a little example of one time series, this is the temperature of sea ice over the course of leg 1. Looking towards the right, 28th of October, the cores are thin, they're much warmer, and then towards December, you can see how the sea ice core is growing and temperatures are much colder. The one thing to pick up from this graph is that this is not necessarily just a completely straightforward relationship in time. There are individual events that don't follow the same trajectory. So this 11th of November, for example, the green curve. So we can highlight events that may affect the permeability and gas flow within the ice. And then we hope that then by looking at the data over the course of all legs, we can quantify the seasonal evolution of permeability and help us understand the gas migration pathways between the atmosphere, sea ice, and ocean. Thank you for your time.
Thank you, Michael. Next up, we have Kerry Harris, who is a PhD student at Dartmouth College. Her research interests include biogeochemistry, stable isotope geochemistry, and polar systems. Kerry is passionate about making polar science more safe and welcoming for all, and she is an outreach ambassador for the MOSAiC expedition and a member of leadership for the Association of Polar Early Career Scientists.
Great, thank you so much for that introduction. So I'm going to switch gears a little bit, and instead of the science I did on MOSAiC, I'm going to talk about being an outreach ambassador for the expedition. So to start off, I want to give you an introduction to the MOSAiC School, which had the goal of training the next generation of polar science communicators. So the MOSAiC School was a 6-week training course for graduate students that took place aboard the RV Academic Fedorov. So that was during leg 1 of MOSAiC, the leg to set up the distributed network. And the 3 goals of the course were to train and educate the next generation of Arctic system science experts, to provide support to MOSAiC science teams aboard the Fedorov, and to then communicate knowledge and experiences gained on the expedition through ambassador projects that would take place over the next year or so. So there were 20 graduate students involved in the program who were trained to be student outreach ambassadors. I'm one of them, and we came from 12 countries and 3 continents and had a really diverse background in terms of our fields of interest, but we all had a mutual interest in Arctic systems. And for 10 of us, not including myself, it was our first time doing fieldwork in the Arctic. So I want to give a quick shout out to Josephine Lenz and Thomas Rakov from AVI, who were our fearless leaders aboard the ship. So the first phase of training first consisted of a crash course in multidisciplinary Arctic science. Over the, during leg 1, we had about 50 lectures, I believe, over 28 hours, all of which are now cataloged online as a massively open online course that Series put together. So if you want to watch any of them, you can. And I see many of the lecturers are on this call. So that was really a wonderful experience. We also got media and outreach training by some of the media professionals on board the ship, and got training on how to translate experience to education from some of the expert educators on board. Phase 2 consisted of supporting the science teams. I was part of the biogeochemistry team, and as we just heard from Mike, I was involved in the ice core team, which was a really great experience. Other ambassadors were involved with ice flow mapping, Boolean sensor deployment, loading and unloading equipment from the ship, and then also involved in weather prediction. And finally, phase 3 is the outreach phase that takes place after our leg 1 had ended and is still taking place now. So between the 20 outreach ambassadors, we have so far done over 100 engagements that range from conference presentations, talks to home institutions, written articles, lessons and events at local schools, and then TV, radio, podcast interviews, just to name a few. And we've kind of had to switch gears a little bit with the pandemic and turn most of our outreach events virtual. So an example of that is me giving this virtual presentation to an exploration group called Exploring by the Seat of Your Pants. So in addition to these kind of one-off outreach efforts, each ambassador also does a year-long outreach project. So I want to quickly highlight 3 of these. The first is a mini podcast called MOSAiC Mixdown by Sam Cornish. So he hopes to bring the Arctic science revolution to life in audio. And so he's created a series of mini episodes, and they're really wonderful. I'm just going to play you a very short clip to give you a sense of them.
MOSAiC.
MOSAiC. Da-da-da, MOSAiC.
MOSAiC. That's my DJ voice. Welcome to MOSAiC Mixdown. I'm Sam Cornish. In a series of very short podcasts.
MOSAiC. MOSAiC.
Okay, the second is a photo book called The Quiet by Thea Schneider from Germany. Thea has a background in photography as well as Arctic climate modeling, and she took a series of just breathtaking photos aboard the ship and has created this coffee table book that I'm giving you a brief preview of here that will hopefully be available soon. And finally, my project is called the Arctic Science Explorer Patch. So I developed a set of science and exploration challenges that are designed to be compatible with the Girl Scout curriculum in the United States to really inspire middle school aged girls to get involved with science and outdoor exploration and to overcome the self-reported confidence and interest gap in science fields that develops around that age. So with that, I want to thank you so much for having me. I really barely scratched the surface of all of the great work the MOSAiC ambassadors are doing. So if you would like to learn more, you can find us, or you can email us. You can find us on Twitter at MOSAiC Embassy, and then you can also check out our webpage on the Association of Polar Early Career Scientists webpage. So thank you so much.
Thank you, Kerry. Our fourth presenter is Gina Joseph, who is a PhD student in the Department of Atmospheric and Oceanic Sciences at CU Boulder, and she's affiliated with the Cooperative Institute for Research in Environmental Sciences. Her research focus is the boundary layer meteorology of the Arctic, and on the MOSAiC expedition, she flew unmanned aerial vehicles, also known as drones, to collect advanced atmospheric measurements of the boundary layer over the central Arctic Ocean and sea ice pack. So welcome, Gina.
Thanks. Can you hear me?
Yes.
Okay, just making sure. Yeah, so as you said, I'm going to share about our observations of the Arctic atmospheric boundary layer that we took with small unmanned aerial vehicles, also known as drones, sorry, during MOSAiC. So I was part of a team flying these drones to collect atmospheric meteorological measurements during leg 3 of MOSAiC. So I was there with my advisor, John Cassano here. We also had a team out there during leg 4, which was Radiance Calmer here and Jonathan Hamilton down here. But besides the 4 of us who were there in the field, we also had a large team of people back home helping with preparations before the expedition, as well as supporting us throughout the entire time that we were out there. So you can see them all here. And then, so some of our main goals with flying the drones for atmospheric measurements were to measure horizontal spatial variability. So we can see how the atmosphere is affected by surface features such as leads or melt ponds. We also wanted to measure the variability of an air mass at a really high temporal and spatial resolution. So we can do that by flying through the same air mass many times during a short period of time and can be able to control where the drones go to be able to do things like this. And we're hoping to use all this data that we've now gathered to improve the weather and climate models of the Arctic. So I'm going to give a brief overview of the 2 different drone platforms that we flew during MOSAiC. Then I'm going to focus in on just one of them that we flew during leg 3 that I've had personal experience with. So here we can see on the left, we have the Datahawk 2, which is a fixed wing aircraft that we flew during both legs 3 and 4 of MOSAiC. And it would capture meteorological measurements. And then on the right, we have the Helix hexacopter, which was just flown during leg 4 of MOSAiC, and it would capture these meteorological variables as well as surface albedo. And so in the map here in the middle, you can see where the Polarstern was throughout different legs of the expedition, but overlaid on top of that, you can see all the locations of our flights. So in green, you can see where all of the Datahawk 2 flights were, and in red, you can see where all the Helix flights were. So we captured a pretty wide range of latitude, flying as far north as 86 degrees. So now I'm going to focus in, like I said, a little bit more on just the Datahawk since we flew it during leg 3 when I was there. So it measured the variables of temperature, pressure, humidity, wind speed, and IR temperature. And then on top of that, we also measured turbulent temperature and wind speed. So that's a very fine scale measurements of those. And we would do a variety of different flight patterns for different goals. So our most common flight pattern was a profile from the surface up to 1,000 meters altitude or cloud-based height, whichever was lower. And we would do this as often as possible when weather allowed to just capture how the boundary layer conditions were each day and how they changed from throughout our entire flight period, which was from about late winter through mid to late summer. We would also sometimes do a loiter at a fixed altitude. So here we can measure how an air mass is changing over a very short period of time. And you would choose where to fly these loiter patterns based on a previous flight if we found a really interesting layer like an inversion. And the last type of flight that we did was a racetrack pattern over leads. So we would fly back and forth over a lead at low altitudes, as well as doing profiles on either side to kind of capture how the lower atmosphere is differing upwind versus downwind of the lead. And here in this figure, you can see one flight pattern from a lead sampling flight. You can see both profiles on either side of the lead. And it's also color coded by surface infrared temperature. So you can see these higher IR surface temperatures in the center here, which is where we flew over the lead, and we have some open water, which is why we have the higher temperatures. So we had a lot of challenges that we had to overcome. And one of those main ones, which a lot of people faced, was the cold winter temperatures. It was especially difficult for us having to do a lot of tasks that are very, take lots of use of your fingers, which can't really do in heavy gloves, but we did overcome. And we also had to deal with lots of crazy ice conditions. So frequent cracks opening up, as well as the fast drift rate of the ice, which we had to adapt our flight patterns to adjust for a moving ice surface as we're flying. But despite all these challenges, we did conduct a lot of flights. Over leg 3, we did 47 flights with the Data Hawk. And here you can see all the temperature profiles from all of those flights. So you can see that we sampled a variety of different boundary layer types. In the winter, we had a lot of really strong surface inversions. And then in the spring to early summer, we had more of a well-mixed surface layer with kind of a dry adiabatic lapse rate that you can observe here, capped by an elevated inversion. So for my personal focus since returning from MOSAiC with my preliminary analysis that I've done is looking at some of the data from the lead sampling flights. So you can see here in the lower right-hand corner, a lead that we flew over on April 30th. And here's some of the data from that flight. So I've plotted the temperature and absolute humidity profiles and then differentiated these between the upwind, downwind, and over the lead segments of the flight. So you can see how the temperature and absolute humidity differs for these different locations surrounding the lead.
Time check.
And so you can't really see a super strong signal so far in my analysis, maybe just at the surface, a little bit warmer and a little bit more moisture in the air. But I'm just going to be digging into this more and trying to tease out that signal to see what we can learn about the impact of the leads on the surface or the lower boundary layer of the atmosphere. So thank you for listening.
Thank you, Gina. And our last speaker before we turn it over to Q&A is Maddie Smith, who is a postdoctoral scholar at the Polar Science Center at the Applied Physics Lab. Her current research uses observations from the MOSAiC expedition to improve representation of sea ice processes in a coupled global climate model with a focus on lateral melting and sea ice albedos. She was a participant on leg 4 of MOSAiC during June through August and also has prior fieldwork experience on field campaigns in both the Arctic and Southern Oceans. So Maddie, go ahead.
Great. Can you just confirm that the screens look okay for you?
Screen looks great and we can hear you.
Great. Wonderful. Thanks so much, Liz. So I'm Maddie Smith. Like she said, I'm a postdoctoral researcher at the Applied Physics Lab at the University of Washington. And I study sea ice and especially its interaction with the ocean. And so I'm going to talk about my experiences on MOSAiC during the summer when the sea ice was melting. And I'm particularly interested in using these observations from MOSAiC to improve our parameterizations of sea ice processes in the climate models, including the ice albedo feedback. So one of my favorite things about MOSAiC in comparison to some of the other work I've done on sea ice was the experience of getting to stay on the same piece of ice for an extended period of time and really getting to know it like our own backyard. So every day we would walk to different parts of the flow to make observations like in this video. This is Ian Raphael, who's a PhD student at Dartmouth. And we would notice little things every day that were different and interesting on the ice. And you really start to intuitively understand how this piece of ice is changing, which is really cool. And this is what we want to capture and characterize with our observations as well. So the thing that generally characterizes Arctic sea ice during the summer when we were there is the melt. So our observations focused around understanding these melt processes. So this includes how the snow is melting into what we call the surface scattering layer, and then how the melt ponds, like you can see in the video where we're walking across the flow, are evolving and getting deeper over the summer. So every day we went onto the ice to measure things, including the albedo of the ice and the melt rates at the ice surface and ponds and in the leads. So I'm going to talk a little bit about those observations. And these components are also particularly important to capture because of their role in the ice albedo feedback. So this schematic kind of shows a number of ways in which that's true. So as the snow melts, you can see on the left, and then the ponds are expanding and covering more of the ice, and also the open water area is increasing. The albedo, which is represented here as alpha, is decreasing. And so this results in more absorption of energy and melt of the sea ice. Many of my measurements focused on understanding the evolution of albedo in specific areas and on specific surface types. This photo shows measurements of the spectral or of the albedo at the same location where there was level ice on 2 dates about a month apart, June 21st on the left and July 29th on the right. So initially the broadband albedo was 0.76. And that means that about 76% of the incoming energy from the sun is being reflected by the snow-covered ice here. In the second video, or in the second photo, that's reduced to 0.57, so about 20% lower. A really interesting feature of the MOSAiC flow that Michael mentioned earlier was the presence of sediment and rocks and shells, and this was a result of it forming initially as landfast ice. This was really cool from the albedo perspective too, because it gave us the opportunity to observe for the first time how the albedo and melt of sediment-laden ice evolves over the summer. So in these two photos, this is of the same location where there was sediment. And in the second photo, it's really obvious how these areas with sediment have melted away faster on the surface. And that relates to the lower albedo that we see here. So on July 27th, the albedo of this area was 0.43, which means that actually more energy is being absorbed than reflected. We can also see the signal of the sediment in looking at spectral albedos. So this shows the albedo at each wavelength. So as a function of wavelength on these 2 dates, blue is on the left, or blue is the earlier, red is later. And so the peak albedo, especially later, once it's melted more, is much higher. And so that's really characteristic of the sediment. So we're really excited to look more into these data. Observations of the albedo also help us understand a lot of the aspects of what we're observing in terms of ice melt from the top and to a degree from the bottom, but we're also really interested in understanding how the ice melts from the sides, where the dark ocean in the leads with a really low albedo is absorbing more heat. So in this photo, I'm making measurements of the heat in the stratified layer, which forms from the really fresh meltwater from the ice pooling at the surface in leads. And our measurements over the entire summer showed a relatively warm layer throughout the summer. And this presence of this layer contributes to more melting at the edges of the flows. And it's also really important to reducing fluxes between the atmosphere and the ocean, provides an interface to biology, for biology to thrive in. And so those are the kinds of measurements that we were making in the photo here. So for me, these observations on ice and the leads were specifically motivated by needs of the climate model, where there are big uncertainties and predictions for the Arctic. The sea ice components of these models, like SEIS, which is what I use and is shown schematically here, have relatively realistic physics. They include a number of different thickness categories in each grid cell, and they have complex thermodynamic and dynamic schemes for ice evolution. But of course, there's many things that could be improved and which are lacking necessary data, which we targeted during MOSAiC. So for example, our observations of stratification that we made in leads where lateral melting is occurring can be used to update parameterizations of the sea ice edge melt, which could be an important feedback. And additionally, we'll use our measurements of albedo from throughout the summer to update the radiative transfer scheme and hopefully work towards better inclusion of sediment in the coupled model, which could have really large regional impacts. So yeah, I want to mention, in addition to my collaborators and advisors who provide a lot of support and guidance throughout the fieldwork, I also want to acknowledge the really immense effort that Avi put into coordinating, getting us there, especially on Lake 4 at the beginning of a global pandemic, and also, of course, NSF for the funding. Yeah, and so as others have mentioned, MOSAiC, as an early career researcher, was a really amazing opportunity to get to work with and learn from so many people in lots of different fields from around the world. So thanks for listening.
Thank you, Maddie, and thank you to all of our presenters. So I have just opened up the chat. So if you have questions or comments for any of our speakers, you can go ahead and type them there. You can also, if you want, use the raised hand function. So if you click participants at the bottom of the screen, you should then be able to see your name, and then there'll be a little button that says raise hand. And if you do that, then you can unmute and ask your question. And again, if you're on the phone, unmuting is *6 and raising your hand is *9. We'll give folks a couple minutes to type some stuff in. Got a question from Maddie from Alec Petty. For model development, how does the fact that this flow formed as landfast ice affect how you might use the data?
Yeah, so I guess it depends what you're relating it to, but definitely the fact that it formed as landfast ice is why we have sediment in it. And so I think that's definitely going to be an important part of teasing apart some questions about the mass balance, how the ice was melting, and also, of course, the albedo. So I mean, I think in terms of analyzing the albedo and for improvements for the model, we really need to think about it more carefully in terms of separating out how these different components are resulting in melt in different places. So I think one of the things that I do want to do is think about using the observations that we have of albedo over these areas of sediment, which are kind of new, to try and more explicitly try and include sediment in the model. And then on a separate note, just also think about using kind of average values over first year and second year ice that don't have sediment to improve the kind of general representation of albedo. So I think we just need to be a little bit more careful about how we treat the data, but I think it actually provides a really awesome opportunity to improve the models even more.
From Olivia Lee, we have a question for Kerry. Do you think the ambassador program would be a good model for other international projects to try to recreate?
Hi, yeah, thank you for your question. I really do. I think the program was a huge success, and I know myself and the other ambassadors really enjoyed participating in it. I think there's something really special about being kind of immersed in a place and in an experience. To be able to kind of take this Arctic science and then translate it into a language that's going to be accessible and interesting to people from lots of different places around the world. And so one of the things we spent a lot of time talking about on board the ship was identifying anchoring phenomenon, or phenomenon that are happening in the Arctic that would be translatable to other locations around the world and to different audiences, whether you're talking to elementary school kids, college students, or other adults. So yes, I think it would be a great model to recreate.
Yeah, may I make a comment on that?
Please.
Yeah, so for answering your question, I'm actually from Taiwan. So for doing MOSAiC, but your researcher is from a tropical island, so I think it's a very good value. And every time when I go home this year and when I present this stuff from MOSAiC, everybody was so astonishing. Why you are standing on top of ice? It sounds so weird for our people there, but it really provides a lot of great values for our youngsters, especially when I present it to some undergraduate students. So I would love to see if there will be more and more this kind of international project can apply this model from MOSAiC.
Thank you. The question for Gina, from Sasha Leidman, can you discuss how your UAS has dealt with taking measurements while moving quickly? Specifically, how did you make sure that the wind measurements weren't influenced, and how did you make sure that the temperature sensor didn't have thermal conductivity lag?
Yeah, so I can answer this question, hopefully, but I mean, we're still working on some of these things. So maybe I don't have the best answer in the end, but to deal with wind speeds, so we know how fast that the aircraft is moving based on, we command it and can measure that. And then we have our wind speed measurements as well. And so by taking the difference between wind speeds in different directions and the aircraft's movement in different directions, we can kind of filter out what the true airspeed is. We're still definitely working on perfecting that and making sure we're getting the most accurate wind speed measurements in the end. As for the temperature sensor, conductivity lag, we have a variety of different sensors on the aircraft, and we actually have for temperature, we do an RSS421 bisala sensor, as well as SHT and cold wires. And so just the RSS 421 is really going to be impacted by the thermal impact of the sun, whereas the other two sensors are shaded and hopefully don't have that impact. And so by having these variety of different ways we're measuring it, hopefully we can figure out what the truth is and figuring out what that temperature, that conductivity lag would be to get the most accurate measurements in the end. Hopefully that was helpful.
Kerry, Paul Overduen has a question. Are there plans for the MOSAiC Early Career and Ambassador Group to continue to meet or work together?
Yes, there are. Yeah, we've continued to stay in touch over the last year. We've had, everything's socially distant now, but we have our socially distant Zoom tea times to kind of catch up and then talk about how our outreach projects are going. And as I mentioned, the pandemic has actually affected kind of our plans quite a bit since, of course, in-person events, while you reach a smaller audience, often are more impactful than virtual events, but we've had to really switch gears and get up to speed quick on some of the best practices in virtual engagements. And so I know one of the new projects I'm working on now is using coding as a way to teach middle school aged kids about the Arctic and also kind of gain some hard science skills that are applicable to many different fields at the same time. And so, yes, this has definitely been an exercise in creativity and yeah, just kind of going with the flow and doing what is necessary to continue to reach our audiences in this changing digital landscape.
Maddie, Ellen Buckley asks, considering you witnessed the melt pond evolution and you're familiar with SEIS, any thoughts on the strengths and weaknesses of the SEIS melt pond parameterizations?
Yeah, that's a good question. Thanks, Ellen. Yeah, I haven't spent as much time thinking specifically about the melt pond parameterizations outside of the kind of optics questions, but I mean, I think something that really struck me being on the albedo flow over the summer was just the huge variability of the types of melt ponds. And so I think we have this really awesome data set now from MOSAiC kind of capturing the evolution of, ice melt ponds on first year versus second year and kind of thinner versus thinner ice. And so I think that there's probably just more we can think about doing to capture some of the variability of that and kind of the impact on how the ice around those different melt ponds evolves. I think something that was really interesting to see just was how some of them really start to get rot. The ice gets really rotten underneath as the melt ponds are warming and melting that ice underneath. And some of these small scale things may not be necessarily important for, or reasonable to include in the models, but are just kind of indicate the huge variability in how individual melt ponds evolve that kind of require thinking about when we're improving the parameterizations. But I'd love to talk more with you about it at some point.
Thanks everyone so far for your questions. And a reminder, you can keep putting your questions in the chat. You can also raise your hand and unmute if you would prefer to speak rather than type. I also want to echo Lawrence Chalmers' comment that as a non-scientist, he said, I have a great interest in the Arctic and Antarctic, and thank each of you for your work and the clarity of your presentations. As a non-scientist as well, I've been appreciating it. Also for those of you watching and listening, John Griffith has been placing a number of links in the chat to ranging from a paper co-authored by Michael to some of the outreach projects that Kerry mentioned to other cool things you can check out. Well, as we wait for more questions, I'm going to ask each of the panelists what you think the most important takeaway from MOSAiC is. So we can maybe go in presenter order. So Fang, not to put you on the spot, but if you'd like to start off, what you think the most important takeaway from MOSAiC was.
You mean for personally or for academically?
Yes, both.
both. For personally, I think this is some kind of memory you won't forget in your life, even though you become very, very old. When you wake up each day, you will still remember how cold it is. When everything is dark and it's super windy, you need to take your rifle, standing outside and protect your bodies, doing the great research. And I think that part of memory is priceless, really. And for academically, I think for those part of data sets, it's just too amazing. And this is my first time when you use your bare hand to send those instruments in the ocean, and you watch it floating away. You think they might not be back forever, but after a year, our bodies from that file, they recover it. Part of them are missing, but part of them, yes, it's on our warehouse now. So each person in our group, we are so excited when we are able to retrieve it from the warehouse. That's a party time. It's a party time for every scientist in our group. Yeah, thank you.
Thank you, Fang. Michael, what about you? You're muted also.
On a personal level, this was a very different type of expedition for me. Most of the time, going on an expedition, I know quite closely the people that I'm going into the field with. MOSAiC was quite different in the sense that many of us got on board not knowing most of the participants that were on the ship. So the first 2-3 weeks, we really had to develop relationships on the spot. And by the end of the 4 months, many of us became extremely close. So not having those close relationships before going to the field was a different experience and challenge for me, but a fun one. From a scientific perspective, many different directions I can go. From the biogeochemistry side, I was impressed just how active some of the processes are, even in the polar night. And I started to appreciate how complex this methane cycling question is. It's not so obvious how fluxes to and from the atmosphere will change with declining sea ice extent. So we investigated many different types of ice on the floe, ranging from first-year sea ice, ice that had survived the previous summer melt, rafted ice structures, so like one ice floe going on top of the other, actively refreezing meltwater pockets. And I think that, like, from all of these different sites, we have different layering of permeable and impermeable structures. And I hope that over looking at the course of the day that we can try and answer questions relating to the magnitude of fluxes that we see.
Thank you. Kerry, most important takeaway from MOSAiC, both personally and academically?
Yeah, I guess I'll say that, you know, experiencing MOSAiC kind of from the eyes of an outreach ambassador or an educator first, and kind of having my role as a scientist to be secondary. It's the first time I've been on a cruise with that kind of role. And it really helped me see things in a different light. And I felt a little bit more free to just be super curious and ask a ton of questions, you know, as opposed to just, you know, having my one focus be my science team and my group, just really feeling like I had the time and the opportunity to pick the brains of, you know, all of these world experts aboard the ship was just a great experience, and one that I will never forget. And personally, I think the biggest thing I'll take away is that this, you know, group of 20 outreach ambassadors, none of us knew each other beforehand. And I just feel now that I have this like amazing network of international colleagues and collaborators, both in education efforts and in scientific efforts, who have all just become really wonderful friends. And so I'm very grateful for that.
Thank you, Kerry. Gina?
Yeah, so I guess I'll start with personal level. So I'm still in the beginning of my PhD. So I have a few years left. So it's really awesome to be able to do something like this right at the beginning of my graduate experience. And on top of that, this was really my first like real field campaign that I've ever done. So it was a really, incredible one for it to be the first one. And just, yeah, I feel like I just learned so much in terms of how to do field work and how to work with the others on board and build a strong community. And so I've learned that this is the type of thing that I'll want to probably do for the rest of my life if I can continue to do exciting expeditions like this. And also I feel like I've just gained a lot of skills that professionally will hopefully carry on through my career as I'm still just starting out. And then in terms of the science, well, for my project personally, what we've done with the drones, flying up that far north is something that does not really happen often. I mean, I don't know of any drone operations as far north as we did at that time of year. So I can't say it's never been done, as I don't know that for sure. But it's a really unique data set for that reason. And so, well, yeah, hopefully we've just learned a lot more that has never been measured before in that type of way. Yeah.
Awesome. And Maddie?
Well, yeah, so something that I think was really awesome about MOSAiC is gonna leave a huge legacy was the really interdisciplinary approach of the science teams. And so we have four of the five science teams represented on this call, and we all kind of presented our own data. But I think that there was a lot of coordination both in the field and in the collection of the data, and also just to kind of learn from each other on the day-to-day. And I think that going forward, we're going to see the huge value of that data set over the coming years, because all that data was kind of very purposefully and mindfully collected in ways that were kind of coordinated. And I think also that's going to make a big impact on how we do science in the future. I mean, I really hope to be involved in a lot more expeditions and field work that kind of takes such a purposely interdisciplinary approach as MOSAiC did. So both personally and academically, I think that was a really big impact of MOSAiC for Arctic science.
So we are just about at the top of the hour, so I am going to wrap us up, but I wanted to say thank you so much to all of the presenters, Fang, Michael, Kerry, Gina, Maddie, all of you for taking the time to present and sharing your stories and your science from MOSAiC with us. Huge shout out to John Griffith from Ceres, who's been doing a ton of lifting on the back end, helping me set this up, and to also just the rest of the IARPC Secretariat staff for support. And then just a reminder of 2 more upcoming MOSAiC month events. So Heist put in the chat the link to this afternoon's collaboration team meeting focused on air, ice, ocean interactions. And then there's also a modeling team meeting on October 22nd. So we hope to see many of you there. And if you need an IARPC Collaborations account, you can sign up for one at iarpccollaborations.org. So thank you again, and hope to see many of you at future meetings.